And if at any point you need to maybe see this again, maybe Coach Winfield can stop this and then rewind it a little bit if need be. So let's say we want to design an efficient cylindrical can. So you've been asked to design a 1 liter cylindrical can. And we're going to specify that we want shaped like a right circular cylinder. So that means it's going to have a right angle as opposed to sort of being slanted, but still being a cylinder. So we're trying to, again, design an efficient cylindrical can. The volume has to be 1 liter. That much we know is true. So before we add some variables to this, let's think about what equation we might use, like the volume of a cylinder is base area, so the base of the area is a circle, multiplied by the height. And we know that has to be 1 liter. In this case, another piece of information is that we're going to be measuring the radius as well as the height of the can in centimeters. So we want to change that 1 liter over to centimeters as well. And in 1 liter, there's going to be 1,000 cubic centimeters, which is why I changed my volume from 1 over to 1,000. The other thing that might be important is the surface area of the can, because if you think about it, that's actually the amount of material that's going to be used is the surface area of the can. And if you think about just taking a can at home and opening the top, opening the bottom, and cutting up the side and unfolding the entire can and making what you might have done in geometry is called a net. It really is going to be 2 circles. So we're talking about surface area. So we have 2 pi r squareds. And the middle is a rectangle. But the long side of the rectangle, if you again open up that can, is really the circumference. The circumference of the can. So that's 2 pi r. And then we're going to multiply that by the height to get the actual shape of that middle rectangular piece. So we're trying to talk about using the least amount of material. We're going to ignore the thickness of the material and any waste that may be in manufacturing. That's pretty common. So we need to find dimensions for R and H for the radius and the height that make the total surface area as small as possible. But again, we can't change the volume. The volume has to stay at 1,000 cubic centimeters. So if we're trying to minimize our surface area equation, the blue one, and we go take a derivative like we did in the last problem, we're going to have a few different rates. In the last problem, we just had 2 variables, x and v for volume. In this case, it looks like we have r, h, and surface area. And that's not going to work out very well because we don't have enough information for all of those different variables. Really, we want an equation in terms of one variable, not two. So I either want to remove the r's or remove the h's. It won't matter. You're going to pick which way is going to be easier. So to do that, we usually go back to some information that was talked about earlier in the problem. So if I look at my volume equation from earlier, we know that volume is actually 1,000. So I have 1,000 equals pi r squared h. And so if I want to eliminate either r or h in my actual surface area equation, then in my black equation there, I can solve for either r or h. Which one would be easier to solve for? To solve for r and get r by itself, or to solve for h and get h by itself? If you solve for r and get r by itself, you're going to wind up having a square root in your problem, which automatically is going to complicate things. It wouldn't be wrong, but definitely more difficult. So I'm going to choose to solve for h, which means I'm going to divide both sides by pi r squared. So that means that anywhere in my blue surface area equation that I see an h, I can substitute in 1,000 divided by pi r squared. So let's go ahead and do that and check out what the equation looks like. So it may look worse to you than what it was before. If we simplify a little bit, it's actually a little bit cleaner. And also now we're just in terms of r as opposed to both r and h, which is going to be an issue. So if we multiply the 2 and the 1,000 together and cancel out some of the r's, this reduces down to surface area equals 2 times pi r squared plus 2,000 over just r, because the pi's cancel, one factor of r will cancel, and then 2 times 1,000 is 2,000. So this is the equation we're going to use to try and minimize. So we're going to find that derivative and set equal to 0. So the derivative of 2 pi r squared is 4 pi r. And the derivative of 2,000 over r, you can make that 2,000 times r to the negative 1, and then use the power rule and get negative 2,000 over r squared, or negative 2,000 times r to the negative 2. Set that equal to 0. So we could say add 2,000 over r squared to both sides to start solving. Multiply both sides by r squared, and that gives me 2,000 equals 4 pi r cubed. So what would r equal? Well, we'd have to divide both sides by 4 pi, and then take the cube root. So that would give me the cube root of 2,000 divided by 4, or 500, divided by pi. That approximates to 5.42. So we never really thought about what the domain was in this problem. So let's go back and let's graph that surface area equation. We're definitely have to adjust the window. If you think back in the original problem, we were trying to minimize our volume. So I want to figure out where this is going to have a low point. And it looks like roughly at 5. And going back to what we got 5.42. So we check out the signs of the derivative of SA, the surface area, around 5.42. Go to the left of it, say choose 5. Substitute that in. Substituting 5 in will result in a negative value. And to the right would be a positive value. So therefore, we're going to have a minimum at 5.42. So the 1 liter can that uses the least material has a radius of approximately 5.42. And that would be centimeters. What if we had to find the height? Knowing the radius? Well, we're going to need to go back to find an equation that relates our radius and our height together. And we can use our volume equation for that. We know the volume again was 1,000 cubic centimeters. And now we know an approximation for the radius. So we can substitute that in and actually just solve for h and get the actual dimensions of the can that would have a volume of 1 liter and minimize the surface area, which would minimize the amount of material that we're going to use. So as you can see, these problems are pretty involved. They're not easy, and they're going to take some time. So I'm going to give you some time to work on these. So the problems I'm going to be working on will be on page 309. I'm going to have you do 1 through 10 and number 14.